All right. I'm Craig Baxter. I'm supporting this project by doing two-dimensional hydraulic modeling and going to discuss how the future flow projections Thomas just talked about impact the models and the fluvial hazards. So going to go through the modeled reaches that we looked at, an overview of the hydraulic model that we used, go through a historic peak flow calculation, how we determined that, then look at individual model reaches, and finally, high-level impacts of the future hydrology on the fluvial hazards. So we chose 4 locations. This is also along the Northeast Entrance Road for various reasons to take a look at the future hydrologic conditions within the hydraulic models. We looked at Warm Creek near the Northeast Entrance, Soda Butte Creek Bridge 1 and 2, where the Northeast Entrance Road crosses Soda Butte Creek. And then we looked at the Soda Butte Creek Lamar River confluence. We're using the HEC-RAS model version 6.4.1 from the U.S. Army Corps of Engineers. We're using the two-dimensional flexible mesh capabilities of that software. We're using, for this set of models, we used the 2020 LiDAR data. Thomas talked about and Jeff talked about 2022 flooding. There is updated LiDAR that we want to use to look at future or post-flood models. We used NLCD land cover data supplemented with aerial imagery to come up with Manning's roughness values. We set up the model using an unsteady flow where we ramp up the flow to the peak flows that were developed in the hydrology phase to simulate a steady flow. And where we have bridges within the models, we're using as-built data to input those bridges. All right, so Thomas talked about changing the historic flow conditions to future projections. And to determine the historic flow conditions, we're taking a known USGS gauge and transforming that to the locations of these models because we don't have gauges at these modeled locations. And so we're using this method and equation from the USGS to determine a drainage area ratio between the ungauged station and the gauge station, and then using regression of coefficients to come up with peak flow values at these individual locations. And those new peak flow values are shown in this table at the bottom here. All right, so the first one we're looking at is this Warm Creek area. It's along Soda Butte Creek, just along the Wyoming-Montana border, just west of the Northeast Park entrance. Modeled about 2.5 river miles here. And the purpose of using this area in the model was this was a potential bank stabilization area. The historic and future flow values are summarized in the table below. See the drainage area at this location, 33.5 square miles with those updated flow values. And so initially we were interested in how flow depths and inundation area was changing as a result of the future climatic conditions. But as you can see, as I step through these slides, this is the 100-year historic flow rate, the 2080 medium condition flow rate, 2080 high. You can tell there is very little change in the inundation area and flow depths when you look at it on a reach-wide scale like this. However, we noticed that there are increases in velocities and shear stresses as a result of these increased flows. And so I'm going to highlight the shear stress changes for the Warm Creek area, looking at this reach where the creek is very close to the Northeast Entrance Road. So focusing on shear stress, I'll just point out that for all of these results, we're going to show maximum values here is 5 pounds per foot square. And so the darker reds are the higher values, the greens and yellows are lower. But you can see the increase in shear stress for the 100-year simulation, looking at historic all the way through 2080 high. Shear stresses increase along the road. Same for the 500-year. Increases in flow rates lead to increased shear stresses along the road. Then looking at Soda Butte Creek Bridge number 1, farther downstream, so larger drainage area to 38 square miles. Modeled about a mile of the river in this location. And the purpose of looking at this location is to ensure the bridge resilience. The bridge is shown there. What we found with this model, looking at shear stress, is that the increases aren't as apparent in this reach. There's some increases here downstream of the bridge, but not as dramatic as the Warm Creek area. Looking at Soda Butte Creek Bridge number 2, again farther downstream. This reach, we're showing some pretty significant increases in shear stress downstream of the bridge for the 100-year and the 500-year event. And then looking at, this is the Lamar River confluence with Soda Butte Creek. This is the largest area that we've modeled using these future climate predictions. We've modeled about almost 9 river miles of Soda Butte Creek and a little over 5 miles of Lamar River. This reach gets inflow from Soda Butte Creek, then Pebble Creek, and then Lamar River. The Lamar River is the largest. It provides the most flow by far for this area. You can see in this table here that flow rates increase almost an order of magnitude downstream of the Lamar River confluence. This reach, we're looking at road resiliency. The part of the model that I'm focusing on here is just downstream of the Lamar River confluence. And can see that for 100-year flows, we're increasing shear stresses along the road, and also 500-year, generally in this area here. So pretty significant shear stress increases. So big picture takeaways for this. We can see earlier on that the spatial extent of inundation does not substantially increase. Flow depths aren't that dramatic when you're looking at a reach-wide scale. So the locations of dry land that's not inundated during a flood event, between existing and future conditions remain mostly the same. However, we see increases in velocity and shear stress, which leads to increased risk of scour along the road, bridge abutments, and that could lead to channel migration or loss of infrastructure. As an example here, we've looked at pre and post 2022 LIDAR to look at changes in elevation. And on the right here is an example of the area near Soda Butte Creek Bridge number 2. And the 2 areas highlighted in red show the blue values are decrease in elevation. So they show decreases in elevation up to or greater than 2 feet. So especially that southern bubble could put the road at risk potentially, just with the changes that happened in 2022.
You mentioned the increase in velocity and shear stress model, but the lines didn't go. Is that because there was just so much weight availability in the system?
So I think looking locally, the flood depths would increase. When we were looking at a reach-wide scale, it's really hard to pick out the changes in flow depth. I think really the takeaway is that the inundation extents didn't really change because the valley is so steep. So you increase flow rate, it's not going to increase laterally, it'll increase in depth. So yeah, faster, higher shear stresses.